about some extension of this amazing result of Kelley Meka to a broader set of linear patterns we call binary patterns. So I'm going to talk a little bit about the history of this Kelley Meka and the problems that came before that, kind of motivate and kind of highlight what the main contributions were. So the main result that started kind of this line of research is due to Roth from 53, and Roth proved that if you have a subset of the interval 1 to m, and if the set is big enough, then it must contain a 3-term arithmetic progression. So let me write it that if this is 3AP standing for arithmetic progression, it's 3AP free, then it must be small. And so the size of A is little of the interval size. And the precise bound that you get from Roth's proof is that actually this is at most, the curly one to hide the constants, m over log m. So slightly better than m. So this is what Roth's proof gives.
Give the straight definition, 3AP, make sure we've got that clear.
So 3AP is A plus B,
Fine.
A plus 2B in A.
Just, okay.
B is not
It counts both
zero.
ends, so
Yeah.
you use the B twice.
B is the jump.
Yeah.
What do you mean twice? Or? Yeah, anyway,
Yeah,
so,
yeah,
Yeah.
you've got a starting point, fine.
Yeah.
And then an arbitrary one is whatever.
Yeah.
And there's just one other, there's just one.
Mhm.
Yeah.
Yeah, so you can have this pattern in A, then A must be small. So before going further into the history, one comment I would make is that, so the way this is formulated is about interval, but we can easily move to finite abelian groups. And so what I would comment here is that instead of 1 to m, we can we'll work with Zn, and I'm going to assume throughout the talk that this n is prime, but yeah, for prime n. So equivalently, we can focus the same on the same problem in subsets of Zn, and the reason is you can kind of embed the interval. So this you can think of as the size m, and you can take the subset A and embed it here, and this is n. And you can pick, just number n. And if you pick n big enough, let's say 3 times more than m, you can make sure that arithmetic progression in Zn, even though they're allowed to go back because of the mod n thing that's happening, they're not going to be able to come back here. So any 3-term arithmetic progression in this subset A as a subset of Zn corresponds to an actual arithmetic progression in the interval n. So there's no difference. Right, in Zn, the problem is that you can have things which don't look like real arithmetic progressions because you're taking this mod n. But because I embedded this in the middle, it doesn't allow that. So we can just equivalently just focus on finite abelian groups, which is kind of very common in this field. So if you carry, now that it's Zn, you can think about other abelian groups. So one thing I want to mention, because just kind of highlight something about this bound, is that if you carry Roth's proof in Z3 to the n, so exact same proof, but in this group of low characteristic, the bound that you get is, so if this is A free, 3A free, then the size of A is actually the size of the group. I'm going to denote it by n divided by log n. So where n is 3 to the smaller. Okay, so you get a better bound here compared to what you get here. Here you lose another log, even though it's kind of the same proof. So there are some technical stuff here in that kind of causes this extra log. And So there's been a lot of work on this. It's kind of one of the main problems studied in additive combinatorics.
Sorry, Ahmed, I
Yeah.
think I'm confused between the connection. You show that if I have any AP3 set in
Yeah.
integers, I can just turn it into an AP3 set over Zn.
Yeah,
The other direction is not true.
no, the other direction,
It's definitely true.
no, so I was saying proving this statement is equivalent to proving the statement for subset of Zn. The two problems are equivalent. And the reason it's equivalent is that like one direction is obviously harder, like because Zn also allows this
Yeah.
other weird free APs, but you can embed this in a slightly larger Zn, and then you don't.
So that was, but then I don't see what is Michelman's result.
That's in a different group,
Oh,
in Z3 to the n. So it's a different
Oh,
group.
sorry.
Yeah. So this is low characters, right? It has a lot of subgroups and stuff, so it makes the problem a bit easier to allow us to get better. So that's one comment I want to make. And another, right, another thing I want to say is about the lower bound. So there is a lower bound which even dates back, predates Rat's theorems due to Berrand. This is from 1946. And it says there are three AP, three subsets of 1 to m size 2 to the minus b log square root log n. And this is the conjectured bound. So people think this is actually the right bound, not what you like. You probably can improve this, right? Yeah.
Should that be density, not size?
Yeah,
That's true, density. So if I want to say size,
Exactly.
yeah, okay, exactly. Right, so this log m is believed to be much larger. It can be improved to a much larger number. Now, there's been a lot of progress on this problem. So there were mentioned some names, just Heath Brown, 84, Semaretti, 90, Bourgain. So these are some of the really key papers in this topic that came up. Each paper kind of introduced a major new idea. Sanders, 2011, and Bloom.
Is that Peter Sanders?
No, Tom Sanders. Bloom, CSASC. This is 21. So let me just say why these last two names that I wrote, these are before Kelley Meka, of course. So this one finally matched what you get from here. So here you got log m. So finally, after a lot of ideas, they managed to improve the integer case to match what you get in this kind of nice finite small characteristic groups. And this was considered a really big breakthrough that they could even go further than this. So this was log m to 1 plus epsilon. So the kind of seemed this was kind of a barrier to a lot of techniques, and finally they managed to push it. And then Kelley and Meka came, and was a really giant leap here. So it's Kelley, Meka, 23. And what they proved is they improved the bound to 2 to the minus omega log m 1 over 12 dot m. So finally got something that kind of resembles this. So instead of square root, they got 1 over 12. So it's really suddenly was a big jump really to the right range of things that we wanted to improve. And this got improved a little bit later. So again, Bloom and CSASC kind of optimized this proof. So they made some observations. So they improved the 12 to 1/9. So that's the current best bound known for this problem. So instead of 1/12, it's 1/9.
Something integer over the.
Integer, yeah.
Okay.
So that's, yeah, so the main focus is on integers. So one thing I say before continuing is that in this setting, actually, now there are proofs that give you polynomial bounds, and they're algebraic proofs. So they use polynomial methods and so on. So it's completely different techniques. They don't generalize, at least for now, we don't know how to generalize them to integers. So this bound's kind of not very relevant. More the interesting cases here, like with this kind of analysis proof. The algebraic bounds are kind of, yeah, very not as robust, and it's a kind of a different world.
And if you say you can get, for those type of proofs, you can get density, which is like n to the 1 minus epsilon, not density, size of n to the 1 minus epsilon.
Yeah, exactly.
What is the construction there? Like, what is analog of Barron's construction there?
So this is about the upper bound, right? So you get,
so
yeah,
at
so the
lower bound,
Barron's,
what will be-
so Barron's construction doesn't really, it's not the best construction there, I think, right? So there you can take, like in Z3 to the n, you can just remove one of the digits, that kind of constructions, you know, like things that have 1 or 2. So those are a polynomial size. So that kind of constructions are optimal, right?
Again, to the 2 there.
So the constants, I mean, yeah, so you get some power. So, but that kind of thing. So it's a very different setting. Yeah. So, right. So my focus is going to be on the thing. Okay. All right. So now let's talk a little bit about, so this part, sparse graph counting. So counting 3 APs is closely related to counting triangles and graphs. So what I want to say is 3 APs in A, kind of there is some kind of correspondence with triangles in some graph. Okay, so let's let me define some notation. So I'm going to use this T3AP of A to count kind of density of 3 APs in A. So this is going to be, I'm going to select the starting point and select a step and the probability that they are all in A. So this is going to be, it's the indicator function of A. So AX, X plus Y, X plus 2Y. So this is a notation that captures the number of 3-term arithmetic expressions. It's normalized, right? So the density of them. So where A, this is not an A. I use identified with the indicator function. So let's talk about this correspondence for a second. If you haven't seen it, it's a nice construction. So let GA be the following tripartite graph. I'm gonna put 3 copies of Zn as my vertices. So this is a copy of Zn, another copy of Zn, another copy of Zn. And I want to construct a tripartite graph such that the triangles kind of correspond to these arithmetic progressions. So the way I'm going to connect these things, X is going to be connected to Y if and only if 2X minus 2Y is in A. X is going to be connected to Z if and only if X minus Z is in A. And Y is going to be connected to Z if and only if 2Y minus 2Z is in A. Okay, so just connect them like this. And why is this an interesting construction? Okay, so what I can do is I can take this and do a change of variables. I can write P3 AP of A as expected value after doing the change of variable is A of 2x minus 2y, A of x minus z, A of 2y minus 2z. Or again, x and y and z. Now I have three variables. They're selected from my group uniformly at random. These two things are equal. If you notice, this is a 3AP. If you add these two things up, it's twice this. So this is another just a change of variable. But make this kind of turns this into a graph counting thing because each of these things are supported on two variables. And that's how I constructed this graph. Okay, I hope it's clear. Yeah, this is just any 3APs counted here, and it's uniformly counted. And then that allows me to construct this graph because all I want is 2x minus 2y to be in A. So that's this edge. I want x minus z to be in A. So that's this edge. And I want this edge to be here, which is 2y minus 2z. So any triangle here gives me a 3AP and vice versa. So these two things are kind of equivalent. So now this is interesting because this gives us a new proof of Roth's theorem using graph theoretic techniques. So 3APs, it's these triangles. And here we have techniques like theorems such as triangle removal lemma. And you can use this to get Roth's little o of m found. So these techniques are very nice and neat, but they use Semmelweis regularity lemma, and therefore they don't give us good bounds. So you get really terrible bounds if you use this, like you get, at least for now. I mean, there's a lot of attempts to improve the bounds for triangle removal lemma. But using regularity lemma gives you terrible bounds. But you can get the little o of m bound. But the thing about this is that they're very robust and they give you this kind of, you don't really do much number theory here or in Fourier or anything. You just construct this graph and then you're just dealing with the graph and the triangles. So you kind of forget about that these are coming from the group or anything like that. So one thing you can do is this triangle removal lemma generalizes to any graph. So there are graph removal lemmas. And they imply, if you use this kind of constructions, you get Roth's theorem for any binary pattern. Now, what is binary? I'm not going to formally write a definition, but if you look at this thing, 2x minus 2y, x minus z, 2y minus z, 2z, it had some properties that they gave us this graph. The particular property is that every linear form involved is supported on exactly two variables. And no two of them share exact same two variables. So I'm not having multiple edges. So if you have something like this, it turns your counting to a graph, subgraph counting. And so you can use this kind of techniques. So an example to have in mind, actually, this was what we first were trying to prove, like in generalized Kelley Meka 2, and we couldn't, was x1. So let's say I'm interested in this pattern, x1 plus, like a K4 kind of pattern, x1 plus x3. Suppose I'm interested in finding non-trivial instances of this pattern. This corresponds to a K4, right? X1, X2, X3, X4. I want any pair of, when I add up to be in A, and I don't want things to be repeated, so non-trivial patterns, I don't want all of them.
So here you're picking x1 to x4 from Zn.
Yeah.
And you want these to for all be in A.
All
Yes.
to be different numbers
Inside.
and be in A, exactly. Yeah, that's what I'm interested in. The same with 3AP, right? You don't want to count trivial stuff where Y is zero. So you just want to have distinct things. So you can ask this question, if a set is free of this pattern, is it a small set? And you can use graph removal lemma to get little r m bound, right?
And in those expectations, whenever you write it, it's from Zn or Zn
Yeah.
minus 0 or.
No, it's actually Zn. So these are randomly independently selected from Zn. Yeah, but the thing is, the cases, the degenerate cases, have very small probability, right? The probability that Y is 0 is very small. So
That's true, but I mean, in an AP free set, that number is 0. So
Yeah,
it's
exactly.
Interesting when
So-
you're counting a bit more than 0.
right, yeah. I mean, I haven't said how we use this exactly in this thing, so I'll get to that now. Okay, so the question that we asked, we're interested to how is, can we get Kelley Meka bounds for binary numbers? Such as this K41 that I just stated, and the answer is yes. So was the project, and yeah, I mean, there are a lot of steps that don't work, so I kind of have to redo the proof in a different way to get this. Okay, so let's talk a little bit about like going back even to Roth's proof. So how do these proofs work? So if A has density alpha, then we expect P3AP to be alpha cube, right? So by what I mean by that is if A is actually a random set of density alpha, then for any x, y, z that you fix the probability that these things fall into A is alpha cube, right? So you get that you expect this to be alpha cube. And what Roth showed, like that's how his proof works, is if this is not true, if this thing is actually deviates from that, so if this is not approximately alpha cube, then there's a large Fourier coefficient. Large non-principal Fourier coefficient from A. And then you can use this large Fourier coefficient. So A is kind of non-uniform in terms of Fourier. Like it correlates with some character, has a large correlation with some character. And that gives you some structure in A. So you can use to do density increment. So density increment in a large AP, and large here means approximately the size is square root n. And density increment means we can go from alpha to alpha plus omega of alpha squared. Okay, so this is kind of the high-level sketch of Roth's proof. That what he showed is you can write this as a nice Fourier expression. And if that's actually deviates from alpha cube, one of the Fourier coefficients of A must be large. So A correlates with some large, with some character, and characters kind of harmonic functions, right? So they kind of have this AP structure. So from that, you can get that A is kind of dense, has some large correlation with some arithmetic progression of pretty large one, like square root n. And then you can just focus on this. This is like another interval, right? Arithmetic progressions are like just intervals, you scale them. So you can go inside this arithmetic progression and repeat this thing. And the key is that your density at each step increases significantly. And significantly is, if you were original density alpha, now it's alpha plus some constant times alpha squared. So if you repeat this many, many times, you're gonna get to one or a contradiction, right? So that's how Roth's proof works.
Sorry.
Yeah.
What is the Fourier? You're doing discrete Fourier analysis?
Yeah, okay, yeah,
On
exactly.
Boolean hypercube.
No, it's a ZN.
On ZN.
Yeah, exactly. Yeah. Yeah. You can also do it in Z really, but I think ZN is nicer. Okay. So this is kind of the sketch of Roth's proof. And all the proofs that I mentioned, including Kelley Meka, kind of follow the same structure. So they all kind of look at the Fourier expansion of A, understand something about Fourier expansion of A, and use it to do some kind of density increment. So they all are density increment based proofs. So a lot of the previous works like this Semeredi, Brown, Semeredi, Bourgain stuff were, instead of this square root n is a big loss, so they improved this to something better, like actually constant size. That's how the earlier improvements came. Okay.
Another detailed question. Is there a way to cast triangle removal lemmas type proof in this language, or like regularity lemma?
So you can do a little bit of spectral theory there, but not, I mean, triangle removal lemma, we don't have good bounds for it because there's no.
But they don't even do something like this. I guess regularity lemma really doesn't do something.
You don't. No, you don't do density increment, but you heard, yeah, I mean, it's a little bit different, yeah.
Sorry, can I why in this density increment that you said you get a large AP? Is it better if the AP is larger?
It's larger because it's better if it's larger because we lose the density each time, right? So you go from n to square root n from, so that's why, like if you Roth's initial proof, you cannot repeat this more than log m steps. So you have to increase alpha very significantly in log m steps. Whereas the newer stuff like Bourgain stuff, instead of AP, they do Bohr sets. So you can get something better or generalize AP like Semeredi. That's what, yeah.
Why did we need to take n to be a prime?
So for example, to do this kind of change of variables and stuff, it kind of helps, yeah. It's not very important, it can work. Yeah, like if true, this is even, right? Like you can't do that. Yeah. So, okay, so some historic commentary is that Kelley Meka the status of the affair was the density increment was this alpha plus alpha omega alpha square, and your set size from n you drop to some n divided by some constant only. So constant. So this is what gives you n over log n kind of found, if you can do this, which was pre-Kelley Meka. They managed to get a little bit 1 plus epsilon, really difficult proof. But generally, this was the situation. So now the breakthrough, at the very high level breakthrough of Kelley Meka is where the improvement comes, is here, really. So instead of adding alpha squared, they managed to add increase of constant times alpha. So here, if alpha is small, alpha squared is pretty small, right? So you have to repeat this many, many times to get a good boost. Whereas they get 1 plus epsilon time alpha. So then, like if you repeat this log alpha times, you really get this very high quickly. And this one is a little bit worse. So you get from n to, so the density goes, I guess, some polylog. We get here some alpha, some constant times n. So here, like you lose some density, but the important where the improvement comes is this. You increase the density very significantly in one step. Okay. Yeah.
So what's the relation between the size of the large AP and like how we with the
So we get a contradiction where the density gets, say, close to 1, right?
yeah.
And you do want to repeat this, right? So if you're starting from some density like this, you increase it a little bit. So you want to repeat this many, many times. But every time here, you're losing your n. It becomes square root n. So so that's, yeah.
Does this type of improvement happens for all choices of n, or there is also lower bound that n should be like large, or you can just go all the way as long?
I mean, there are constants hidden, but yeah,
Just-
doesn't, yeah. Okay, so now let me talk about graph counting. So there's kind of a similar situation there. So there's a theorem from 87. So independent, kind of two works that started this quasi-random graph business. It's Thomason and then Chung, Graham, and Wilson. So the notion of like pseudo-random graphs and stuff come from these two papers, really. And you can, basically they prove this thing among many other things. So if the density of your graph H in G deviates from what you expect, so here H has M edges, and alpha is edge density of G, right? So if G is a random graph with edge density alpha, you expect this to be alpha to the n. And what they say is that if this deviates from what you expect, but say epsilon times alpha n, then there exists two sets, S and T, of subsets of VG. So one is that they are large, T of density constant, so omega 1. And 2, you get density increment. So if you select your vertices from pair ST, then the edge density is omega of n minus 1. Okay, so if you look at the adjacency matrix of A, what this says that you can find sets, let's say this is S, this is T, such that here the density is different. So like what you get here is different than alpha. So you get two large sets, S and T, they are pretty large, constant fraction of the rest is such a, when you look at between them, what's happening is different from alpha, which is the general edge density. So you get some kind of deviation here. So this is one notion of pseudorandomness, like irregular pairs that comes up in regularity lemma and stuff, in formulations of regularity. So this is just telling me this density is different from alpha, but I can actually get a density increment out of this. Can anyone see why this absolute value is not a problem?
The average is alpha if somewhere you're higher.
Exactly. So S and T are big sets. So if this is much less than alpha, somewhere else I have to be larger than alpha, right? So you can, for example, partition into 4 parts and so on. So this actually gives us, actually we can say, increase. So this expected value is T of A is larger than alpha plus. Maybe different S and T. So this is really the analog of what's happening with Roth. Instead of going to sub-arithmetic progressions, here we go to sub-bigraphs, and you get some kind of density increment.
So the size of S prime and T prime should also be large.
Exactly. Yeah. So this is like they're constant size. You can get it constant size.
And roughly what is dependence on epsilon here?
I don't remember. Yeah. It
But
shouldn't be
that
too
gives
bad.
you- Is it the same as what you get?
Actually, it
from
might be
STOC?
here just the same constant or something like epsilon maybe over m, something like that. Okay. Yeah. It's a very simple theorem. I mean, the paper proves a lot of things. This one has a very short. But you see, it's the same phenomena here that if you have a triangle, you get alpha square here. So it's not much of density increment, even though these are really big sets. So the fact that these are big sets is good, but the amount of density increment is not that great. So let me give you, so this is one of the theorems that we have in the paper, and it's kind of a nice observation, but it's not completely useful. It's a kind of an easy thing. But here is what you can get, kind of an improvement of this. You can say, oh, by the way, this is necessary. If you want large sets, you can construct examples where you can show you can't do better than this. But what you can get is the following. So if T H of G is larger than what you expect, then you can find exists ST, their sizes are, their density is omega of alpha to m plus 1, and you get very good density increment. Okay, so this is perfect for us. If this condition holds, if you have too many copies of H, you can actually get relatively large sets. So they're not constant size, but they're still pretty large, polynomial size, and you get very significant density increment. So unfortunately, the other side, at least for this theorem, is not great, which is, what if this was actually like in the case of say 3AP free, it's not, you don't have too many triangles, you have few triangles. So what if this is less than 1 minus epsilon to the alpha m? Then in this case, so the first thing is the same, but you get only density decrement. So you find some kind of relatively large SMT where this density actually drops a lot. It's not great for things like Roth theorem because you can't repeat this in any sense, right? So you don't know what's next time happening. So if
So
you,
the
yeah.
averaging argument won't work because the sets are too small.
Yeah, exactly. Yeah. So this is this doesn't give you exactly large sets because these are not constant size anymore. They're kind of smallish. Yeah. Okay. So this is actually so this is the happy case here. So if we could get this, we would be good shape. This is not so great because we're actually decreasing the density. But this is going to be useful. This part is going to be useful for the main result. Let me just quickly tell you how you would prove this. It's kind of intuitively, it's not a very surprising theorem. So we have this edge, let's say a triangle or something, and we know there's, let's say, focus on this. There's a lot of copies of edge here. So let's just single out one edge in edge, and let's call this edge prime. Now, let's look at a typical copy of edge prime here. So some embedding of edge prime here. Now, if things are not uniform here, you can apply induction. Otherwise, what you expect is that you should be able to extend this to copies of edge in many, many ways, because we know we have a lot of copies of edge, right? So that means there are many candidates for these two vertices A and B. So these are candidates for A, these are candidates for B, such that if I pick something from here, there's a good chance I'm going to get a copy of edge. But that means there should be a lot of edges here. So these are going to be your sets, S and T. Okay.
So can you say again, what was this mapping H prime to H prime?
So I know I have a lot of copies of H in G. So therefore, let's first map the first part of H, this H prime to G.
And it's like somewhat, you just took an edge out.
Yeah, it's just arbitrary edge. So this is let's look at the typical embedding of it is here. I'm saying typically you should be able to extend this to a lot of copies of edge. And because there's an edge here, it will give you a lot of edges between these two. So that's the intuition. Yeah.
Sorry, so you need to have like low density for H prime, right?
Yeah, and if you have high density for H prime, then you can apply induction on H prime. That's how it is. Yeah. It's an induction. Okay. Now let's get to the main thing, which is how can we resolve this issue? So let me write out the main graph theorem. So if G is regular means degree regular. So all the vertices have the same degree. Then if this thing is large, then you can find S and T such that their densities are 2 to the minus log square of alpha. And you get density. Okay, so this is kind of the main graph part of the proof, which is we go a little bit further in the density, so it's not as good as polynomial, but it's not too bad. You just, instead of log alpha, we have log square alpha, and you get the density increment that you want. Okay, Okay, so how would we prove something like that? Ideas. So one thing to observe is if okay, so we are interested in this thing. I can assume that this is the same as applying this th to a minus alpha. Okay, so I'll do these steps for triangle in a bit, but okay. So what do I mean by this? This th is, let me write it actually. If I ever wrote this. This is the expected value. You take all the edges of h, and then you apply a to x u x b, right? And these are the variables x u for all u and b. And this is the formula counting density of this graph h in a. Now it's a function of a, right? A is, you can think of it as a function. You can put any function that you want. And I'm saying if you put a minus alpha here and you expand it, you're going to get a lot of terms. But if any of the terms is not uniform, you can apply the induction hypothesis to them. And if they're all uniform, these two things are kind of the same. So you can focus on this thing instead. Does it make sense? Like we do a lot of induction here. Like if the expansion, like you're dealing with subgraphs of h there. So if any of them is not close to alpha to whatever it should be, then you can apply induction hypothesis. Okay, so that's, I mean, this is not a very important thing, but kind of let's talk about this K22 graph. Which is the same as C4. What if this H was just K22 or C4, cycle of length 4? Then this thing, let's look at this spectrally. This is just density squared plus, this is really just the fourth moment to the power 4 of the eigenvalues of A. Okay, so alpha is the principal eigenvalue, like the first eigenvalue, and then this is just trace of a transpose, a transpose, like if you're counting C4. So it has a nice formula like that. Okay, so for a graph like this, TH actually cannot be smaller than alpha to the 4, right? Right, we had this theorem of 2 cases, but for some graphs, actually this case can never happen. And K22 is one of those graphs. You always have more than what you expect. Now, you can prove a similar theorem for K22. So, maybe a different alphabet, that's one. Okay, so K2P also has a similar property that if this thing is large, then actually the density is larger than what you expect. So you can kind of apply the previous theorem that we have for any P. Okay, and this one, this doesn't have a nice like eigenvalue formula like that, but it's something that follows from positive semi-definiteness and those kind of properties. So it's kind of a not a difficult thing, but it's a really key thing in this proof and the Kelley Meka's proof too. Okay, so let me. Okay, so let me just sketch the high level steps. So our starting point is that this thing is large. But this, as I said, we can assume this is approximately th of a minus alpha. And then from this, so using Holder's inequality and regularity, you can get that tk2p of a minus alpha larger than epsilon prime 2p. This 2p, by the way, is the number of edges, right? Okay, 2p. That's right. And then okay, so this is kind of the high level of how you can get this density increment in the graph case. So what does this say? It says if the number of copies of H in G is not correct, then you gotta have a lot of K2Ps. So even like, let's say you're free of copies of H, then you must have a lot of K2Ps. Then you can use the previous theorem, because you have a lot of that, you can get the density increment. Okay, and here the P is important. So this P is gonna be where you apply this Holder inequality, is coming from that. It's gonna be log of 1 over alpha roughly. It's not any P that comes from the Holder inequality. Yeah.
So I didn't get what happened. So you got a density increment.
Yeah.
But your goal was to show that number of K2Ps are very large.
So I'm not proving this lemma. This is the sketch of, sorry, yeah, I didn't prove it. This is a positive semi-definite proof. This is a sketch of this proof using this lemma.
Density increment there.
Yeah, exactly. Yeah. So I can stop here, or if you want, I can sketch just a step for the triangle. I don't know. What do you do, 1 hour or 15 minutes?
Let's take a break.
Okay.
And if people stay, then you can do the triangle.
Yeah, okay.
So
That's like
maybe
another
after-
5